Okay, so we're going to move on to KSP and everything involved in KSP, but in order to understand that, we have to know what KSP is first. And KSP is essentially your constant of your solubility product. And like every other K that we've been dealing with thus far, it's your concentration of products over your concentration of reactants. Yeah, so like every other equilibrium thing we've dealt with. And with KSP, so a high KSP equals, well, a high KSP gives you a more soluble substance. So it just means that the higher your KSP, the more soluble your substance is in water, and the lower your KSP, the less soluble your substance is. So if you have a high KSP, it's highly soluble. If you have a lower KSP, it's less soluble, meaning it takes more time for it to dissolve in water. Right. So when you're writing your KSP expression, so it's a solubility product, just writing it down so you guys don't forget. Solubility product. Right. So it's known as a product essentially because all you end up doing is multiplying. So if we take the generic expression AB yields A plus B minus, these are aqueous. But with KSP, we're dealing with salts, and like normally your salts are solid, right? Like you can hold them, you can see them, you can taste them if like they're not deadly, like sodium chloride. Don't taste the stuff in lab. But anyway, as I was saying, these usually end up being solid. So when you're writing your KSP, your concentration of products, yeah, you have your ions, right? And those are aqueous, so they count. But your reactant is a solid, it's a condensed state, so it's just 1. And when you divide anything by 1, it's the same number. So you just end up with the expression that is just the product of your products. So yeah, that's weird saying product twice, but it just ends up being a multiplication. So therefore your K is a product and not a quotient, as opposed to other times where you actually would divide it. So yeah. So we can do some examples of writing reaction quotient, not reaction quotients, KSPs, so that you guys get what I mean by it's just a product. So let's take, for instance, the salt magnesium fluoride. That should say solid. Yeah. So this would break apart into our magnesium ions and our fluoride ions, but we have to balance it since we have 2 fluorides here, we have to have 2 fluorides here. So our KSP is equal to our concentration of magnesium ions times the concentration of our fluoride ions. And remember, for equilibrium, our coefficients become our exponents. So that's my KSP expression for magnesium fluoride. So then let's take silver chloride. This is also a solid. That breaks apart into my silver ion and my chloride ion, so that my KSP is equal to the concentration of silver ions times my chloride ion. And yeah, I mean, writing the expression is pretty easy because your reactant's always going to be a solid, so that doesn't even have to matter in your expression. So all you do is you multiply the concentration of your products, but make sure that your reaction is balanced because the balancing becomes our coefficient, like I said. So yeah, it's not too bad writing the expression. So then what we do with KSP is that we can find solubility and molar solubility using KSP, or vice versa. And essentially what that means is that if we find the solubility of a product, we can find the molar solubility solubility, which means we can find our concentration of ions, which means we can find our KSP, and this all works in reverse also. So we can use KSP to find concentration, which we can use to find molar solubility, which we can use to find normal solubility. And the difference between solubility and molar solubility is that solubility is found in grams per liter, and molar solubility is found in moles per liter. So I know that's kind of confusing, like that things go from one to another, but I find it easier to explain kind of just by doing a problem. So we're going to do an example. So we're going to try to calculate the solubility. Calculate the solubility of calcium sulfate, which is CaSO4, given the KSP is equal to 4.93 times 10 to the negative 5. Oh, my negative is very high up there, but there we go. Times 10 to the negative 5. So we're going to do our step 1 is just going to be writing our expression, well, our equation. And that's a solid. Would break apart into our calcium ions, which are aqueous, plus our sulfate ions, which are also aqueous. Right. So then from that, we're going to find our, well, we know our KSP, but essentially with these is that we can replace these with x's, because if we were doing an ice table, these always end up being an x, and this doesn't matter because it's a solid, right? So 0, 0, plus x, plus x. And that's just so that we can simplify what works after that. But okay, so let's do step 2 as writing our KSP expression, which is going to be equal to our concentration in calcium 2 plus times SO4 2 minus, right? So then we can carry on our step 3, and that's going to be to solve for concentration of ions, which we were given our KSP, which is 4.93 times 10 to the negative 5. And that's going to be equal to this that we wrote over here. But since I gave them the x, we can essentially just do x times x, which is also equal to x squared. So we have 4.93 times 10 to the negative 5. And we take the square root of that, which gave me 7.02 times 10 to the negative 3 is equal to x, which is our concentration of our ions. So then we can find in our step 4, we find our molar solubility by using our molar ratio. So essentially what we have here is that we have 7.02 times 10 to the negative 3 moles per 1 liter of, let's say, calcium, just because that's the first one that I saw. And it's a 1-to-1, so like they're going to have the same value, so it doesn't matter. So essentially with 1 mole of calcium, we make 1 mole of calcium sulfate, right? Because it's 1-to-1-to-1 in the coefficients. So we get rid of moles of calcium, and that's how we get that we have a 7.02 times 10 to the negative 3 moles over liters of calcium sulfate, and that's our molar solubility of calcium sulfate. So then finally, our step 5 is going to be just to find solubility using the molar mass. Find solubility, which is given to you in grams over liters, so we're just going to convert. So we have 7.02 times 10 to the negative 3 moles of calcium sulfate. Oh my god, that line is ugly, I'm sorry. I don't think that's any better, but okay. And this is over 1 liter. So then 1 mole is equal to about 136.14 grams. So we end up with 9.56 times 10 to the negative 1 grams per liter. And that is our solubility of calcium sulfate. So yeah, so you guys see how we used our KSP to find our concentration of ions, and then from concentration of ions we found our molar solubility using the molar ratio. Then with the molar solubility we found our solubility. So it really is just, you can work backwards to find these things or forward. So yeah, it's not too bad in my opinion. So let's do one where we're working the other way around essentially. So we're going to do solubility to KSP. This is very slow scrolling, but okay. So let's say that the molar solubility oh my god, solubility of barium fluoride is 0.58 moles per liter. What is the KSP? So we're starting off with molar solubility, so we don't have to worry about the solubility. But what we do have to worry about is our concentration of ions, right? So we have barium fluoride, which is our solid, breaks apart into barium 2 plus fluoride, 2 fluorides minus, because we're balancing, right? So then I'm going to write the KSP over here. KSP is equal to barium times fluoride squared, right? But then once again, if we were doing our ICE table on this, and I'm saying this because we're going to have to use it, so 0, 0, plus x, but in this case it's 2x because we have our coefficient of 2, right? So x and 2x, so KSP is equal to x times 2x squared. So then this is essentially 5.8 moles per liter, and that's the molar solubility of this. So this 2x and the 1x in front of here is essentially our molar ratio that we would use to plug in to find our concentration of ions. So if we were to do 0.58 times 2 times 0.58 squared. And then we would solve for that to get our KSP, which I have to do because I forgot to multiply by 2 when I first worked this problem. 2.58 squared times 0.58. So then our KSP would be 0.78. I am holding my pen backwards. 0.78 would be our KSP. So yeah, essentially putting these two in front of the x here is what gave me my molar concentration. Well, my concentration of ions, because now it's times 2, and then we just plug it into our KSP formula, which this would be squared. Oh, yeah, that should be fine. So then you plug that into that, squared times 0.58. Yeah, just double checking my work here, guys. But yeah, so 2 times 0.58 squared gives you the KSP of 0.78. So yes, this isn't too bad. It really is just kind of knowing the ratios of things. So I'm going to stop this video here because then it's going to get way too long. And then the next video is just going to be solubility effects and your Lewis acids and bases. Yee.